This is the second of 3 videos about the well-posedness of the nonlinear Schrodinger equation in high regularity Sobolev spaces. And today we're going to be focusing specifically on the uniqueness aspect of local well-posedness. So just a quick reminder, the nonlinear Schrodinger equation that we're studying is this equation, I dt plus Laplacian u equals u mod u p minus 1, and we're given initial data at some time t0 in hs. And throughout we're going to be taking s greater than n over 2 and p to be an odd integer. So in the previous video, we proved the local existence of solutions to this problem and also the continuous dependence of those solutions on the initial data in hs. So today we come on to the third aspect of local well-posedness, and we're going to show the uniqueness of solutions in this solution space, which I'll come on to in more detail in a moment. So just to be clear on what we know so far, in the last video we proved the following theorem. So under the conditions I said above on P and S, we have that for any initial data u0 lying in hs, there exists a local solution u to the nonlinear Schrodinger equation on some time interval around the initial time t0, and the width of the time interval depends only on the norm of the initial data in hs. So we have this relation, and in particular, as the norm of u0 in hs gets larger, the width of the interval gets smaller. So we only have a smaller time on which we know a solution exists. Moreover, we have a quite weak form of uniqueness for the moment. We have that u is unique in this space, which I call b2u0hs, or norm of u0hs, and the interval t0 minus t, t0 plus t. So this is a space of continuous functions on that interval into hs, whose norm is always less than twice the norm of the initial data. And so I give this for a general t, which is less than or equal to this t of u0 above, on which we constructed a solution. And this just says that we have uniqueness on any sub-interval in this space, not just on the actual interval. This is a bit of a weird technicality, and you can sort of ignore it, but it's just something we're going to use in the proof of uniqueness, so I included it fully there. So we already sort of have uniqueness in this very small ball in the space of continuous functions into hs, but it's very natural to ask if we can get continuous in the whole space of continuous functions into hs, because it would be annoying if it turned out actually we had other solutions, but they were just had bigger hs norms. And indeed we do have uniqueness in the whole space, and that's what we're going to show today. So to make this precise, we're going to prove the following theorem. So under the same assumptions on s and p and t0 and everything as before, if we let u0 lie in hs, then if I is any compact time interval, or actually we don't even need it to be compact, containing this initial time t0, and u and v are both functions which are continuous on this interval into hs, and strong solutions to the nonlinear Schrodinger equation with data u0, then in fact we have that u equals v. So this is not just on the interval that we just constructed a solution on, this small one whose width depends on the size of u0. This is actually any interval on which we have a solution. We have uniqueness in the space of continuous functions into hs. Okay, so let's prove this. Well, it turns out that it's actually fairly simple to prove this locally. So by that I mean that if we know that u and v are equal at some time t, we can show that they're equal on some neighborhood of t. So suppose this is true, then we can draw these functions on this diagram on the right. So say u maybe looks something like this. So our solution u going through ut at time t, and maybe v looks something like this. So on this graph I've got time on the x-axis and the norm of the solution on the y-axis, so that you can really think of it just as the solution. So using the local well-posedness theory, which is all we have available, we know already that there exists some time t depending on the size of u at little t in HS, so that the solution is unique in this ball. So this b t2 norm of u t in HS on the interval t minus capital T, t plus capital T. And as I commented when we stated the proof of the local existence theorem, this is whenever t is less than or equal to this special t depending on the size of the norm. So we can draw these times on our diagram. So we have t plus norm of u and some t minus t of norm of u, sorry. So we know that on this time interval, and indeed any subinterval, there is a unique solution whose norm is always at most twice the norm of u at time t. The problem is, as we can see from the diagram, we don't know that u and v lie in this ball. So you can see here, v has rapidly grown to have norm greater than or equal to twice that of u at time t. So no longer lies in this ball and we can't apply the uniqueness theory. However, because u and v are both continuous into HS, we know that if we work in a smaller time interval, so we can go, it looks like up to here, so t plus some smaller t, they do lie in the ball. They do have norm at most twice the norm of u at time t by continuity. So we can apply the uniqueness theory from the local well-posedness, the local existence result. So just write that down. Since u and v are continuous in HS, there exists some t, or strictly greater than 0, which is less than or equal to this special time t of u of t, so that both u and v lie in this ball, b 2 times the norm of u t in HS on the interval t minus t, t plus t. But we know that in this ball, solutions are unique. So if u and v both lie in this ball, then we must have that u and v are equal when restricted to the smaller interval t minus t, t plus capital T. And as I said, we've shown that u and v are equal locally around time t, on some neighbourhood around t. It's just worth noting that if we had the u at time t was 0, we'd have to be slightly more careful, and we couldn't work in this ball of radius twice the norm of u at t, because we wouldn't have by continuity that there was some small enough time in which they still lay in the ball. But we could instead construct a solution. We could replace this above here with the ball of radius 2 epsilon for any epsilon greater than 0, and work on this t epsilon instead. And I'll leave you to check the details, but yeah, it all worked out fine still. Okay, so we don't need this. So this is all well and good, but the problem is we only showed the uniqueness in some small interval around this time t. Now you could say, okay, so now we go to the endpoint of the new interval, this time t plus t, and we do the same thing because we know u and v are equal there, so we can find another interval around t plus t and show that they're equal there, and then we can go to the endpoint of that interval and do it again, and so on, until we get the whole interval. The problem is this won't work. So the reason is we have no control over how big the new interval will be. In fact, the norms, as we saw at first, that the norm of u is just this norm of u of t, by the time we get to the endpoint of this interval, the norm of u could have gone up to twice that. So by the time we get to the end of the next interval, it could have doubled again and so on. And so each time, the existence time you get and the time on which you can apply our uniqueness from the local existence theory gets smaller and smaller and smaller. And in fact, there's absolutely no reason to believe that we're eventually going to be able to cover the whole interval I with this argument. You're probably just going to bunch up and get stuck at some smaller time which doesn't cover the whole interval. So when you run into these kind of problems where you're trying to iterate things but your times don't have enough control and you're getting bunching up and this kind of thing, personally I find that a very nice, neat way of solving your problems is to use a continuity argument. So what I mean by this is we define J to be the set of times in the interval where u and v are equal in the sense of HS. And we want to show that J is both open and closed in I, because J is clearly non-empty, because we know that at time t0, both u and v are equal to the initial data u0. So then J will be non-empty, open and closed in the interval I, which is an interval, so connected. So by topological properties of connectedness, J must be the whole interval I. So we have uniqueness on the whole interval I. Well, equality of u and v on the whole interval I. So why is J open? Well, that's exactly what we just proved. We proved that for any t in I, or at any point t in J, where u and v are equal, we can find a small interval around that time t on which they're still equal. So by what we just did, we already know that J is open because we found a neighbourhood of any point in J which still lies in J. Why is J closed? Well, one way we can write J is as the pre-image under the function u minus v of the set 0 in HS. U minus v is continuous from the interval into HS because u and v both are. So this is a closed set because 0 is a closed set in HS. So this is it, we're done. We already know that J is open, we show that J is closed very trivially, and so because the interval I is connected, J can't be both open and closed without being the whole set or empty, which it isn't. So that's the end of the proof. Just to finish this video off, I'm going to mention this corollary of uniqueness, which is that the maximal interval of existence, I star, is well defined. So what is this? So if you forget this definition for now, I star is the maximal interval on which a solution exists. So we constructed U on this small interval containing the initial time t0 where we could do Picard iteration, but really it should be able to extend much further. And indeed, we can do this. So if we define I star as the union over all intervals so that there exists a solution which is continuous into HS on this interval, then now by uniqueness, this is well defined because whenever two of these intervals overlap, the corresponding solutions should be equal on the overlap because of uniqueness. So this allows us to properly extend any of these solutions to the full interval I star in a well-defined manner. So this is just nice to know that there's a proper way of defining a maximal interval and there's not multiple different ways you could extend your solution U in the space of continuous functions into HS, which is where we're always working. Okay, so just quickly, some exercises if you want to check you've understood everything properly or just do some more maths. So these are both really just quite well-known results that are definitely good to know, even if you don't do. So the first is that this maximal interval I star is open. This is not very difficult to check just because basically if it was closed, then you would be in HS at the endpoint and you could extend your solution beyond the endpoint. The second is to show that if your interval is finite, at least in one direction, so it's centered at some t0, if it suddenly stops at some t plus, then the solution must blow up in HS. It can't just nicely stay bounded and then suddenly stop for no apparent reason. It has to have a proper explosion of the norm. And you can actually even find a sort of rate of blow up in terms of the norm of U has to be greater than or equal to some function which depends on the distance you are from the endpoint. So yeah, have fun doing the exercises, and I'll see you next time to finish this off by discussing the persistence of regularity of solutions.